Another topic that we want to review before getting into our vector algebra in earnest is something called a unit vector. So to describe a unit vector, let's first just consider some vector A. And so I'm going to put an arrow above our A to indicate that it's a vector quantity. And let's say this A has some magnitude, which we can write as, we can use our sort of parallel vertical bars here to indicate it's the magnitude, or we can just write A without the arrow above it. And we're of course going to assume that this magnitude is greater than 1. So if we want to define something called a unit vector along A, so a unit vector along A, we can define that as U sub A with a little caret on our U is equal to the vector A divided by the magnitude of A. And so it's that simple. And so by design, what we can notice then is that our magnitude of our unit vector is equal to 1. And we can also notice that our unit vector, U sub A, is in the direction of our vector A. So it's in the direction of A. And then one other thing that we can observe is that we could define our vector A as being equal to the magnitude of that vector A in the direction of our unit vector, U sub A. So why do we want to bother with this unit vector? Well, our unit vector is going to be useful for describing vectors in terms of its component parts. So useful for describing vectors in terms of component parts. And that'll become a lot more evident later on, but we'll see that even in some of the examples in the following pages as well. So let's look at sort of a specific case. Let's say we have some vector A in a particular coordinate system. So vector A in Cartesian or rectangular coordinates. And again, we're going to come back and we're going to talk about our coordinate systems in more detail in the next unit. But for now, let's just talk about our Cartesian coordinate system, which is the one that most people are going to be familiar with. So if we have a vector A in Cartesian coordinates, we can represent it one of two different ways. We could have angle brackets, and we could say we have some component in our x direction, a sub x, some component in our y direction, a sub y, and some component in our z direction, a sub z, and then we close our angle brackets. Alternatively, we could write this as a sub x in our unit vector in the x direction plus our y component of A in the direction of our unit vector in the y direction plus our z component of A in the unit vector for our z direction. So if we want to take a look at what this looks like graphically, we can sort of plot a 3D axis here. So I've already got one here, so that's a little neater than if I were just freehanding it. And so we see we have x, y, and z directions. So let's assume that all of those components are positive. So let's just come up here and say, assume all of these are greater than 0 for our plot below. And so what that means is that we're going to have some component along our x direction because our u of x is going to be in this direction. So I make this a little larger to see it easier. So we have some component of our A in our x direction. So this would be our AX in our unit vector x direction because our unit vector x is in the direction of our x-axis. We then have some component of A which is in our y direction. So maybe something that looks like this. So this would be our AY in our y direction. So AY times our unit vector in y. And then we have some z direction, which is going to get out of our xy plane. So maybe we go up somewhere like here. So this would be AZ in our direction of the unit z vector. So now if we put all three of these components together, and this is something that we'll come back to in the following videos, if we drew our vector A, it'd be from our origin to this point here, So we would have something that looks like this. But as we're going to see for several operations, it's going to be useful to be able to write these in terms of our component parts. And that's true for our Cartesian coordinates as well as other coordinate systems that we're going to look at later. But we see basically we've broken it into an x, y, and z directions. One other thing to note is if we wanted to know the magnitude of the vector A, we can find that as well. So magnitude of A is given by A is equal to the square root of ax squared plus ay squared plus az squared. And so this is for Cartesian coordinates. Again, we're going to come back and talk about Cartesian coordinates in detail, or coordinate systems in general in detail a little later on. So a couple of things I want to mention relating how the textbook notates things versus how I'm going to do it in the notes. So your textbook, instead of using this notation here, is just going to use normal parentheses. So it would have ax, ay, and az. Personally, I don't like using that because I think that's easy to get confused with just a point, ax, ay, and az. So whenever we're dealing with vectors, I'm going to be using those angled brackets as opposed to just normal parentheses. One other difference in notation between my notes and the book is this definition for our unit vector. So the book, it actually uses a lowercase a, and then in this case, if we're doing a unit vector along this vector capital A, we'd have an A subscript and just an arrow. The only reason I do this a little differently is personally I prefer this U parameter because of course we're talking about a unit vector, so U makes sense. And I also like using the little caret above it because that helps it sort of stand out from any other vectors that we might have in our equations. So again, the only reason I point that out is if you're going through the book as well, just so you can note the differences between what I have here and on Canvas versus what you see in the textbook.